Hey everyone, in this video, I'm going to briefly go over the SN2 reaction mechanism. And so before I begin, I really just kind of want to show off this GIF that may help you visualize what's going on. And so I'm going to switch over my screen. All right, so what's basically going to happen is we have this molecule here, and the red group is going to indicate our leaving group, and then the green is going to indicate our nucleophile. And so at the point where the green and the red are almost attached to this carbon right here, they aren't attached at the same time. But if we want to draw the transition state, we'll go ahead and draw the partial bonds, and I can go ahead and show that. So this is basically what happens. So the green will come in and attack from the opposite side that the leaving group is on. And that basically happens at the sigma antibonding orbital. And so the sigma orbital is being used to form the bond with the leaving group, and then the green comes into the antibonding opposite side and basically kicks off that red molecule. So I'm going to switch over to my iPad and we will continue. All right, so just to kind of go over a few things about the SN2 mechanism. So I drew it kind of right here, and what basically again happens is the nucleophile will come in and attack at the sigma antibonding orbital of this carbon right here, which sometimes is referred to as the alpha carbon. It's the one that has the leaving group. And then these sigma electrons will go and sit with the leaving group. And that brings up a good kind of point because our leaving group needs to be stable with an extra set of electrons. You know, when we kick off the leaving group, it'll become an anion like this. And so you'll see a lot of halogens as leaving groups like chlorine, bromine, and stuff like that. However, I will mention that this may be brought up later, but we have something called a tosylate, and that could also act as a good leaving group. So we can have our nucleophile come in, and then our tosylate will be stable enough with the negative charge that it acts as a good leaving group. So with the SN2 mechanism, we do not go through a carbocation. And this is really important because this does not kind of open the door for rearrangements, shifts, expansions, stuff like that. Right as the nucleophile attacks, the leaving group leaves, and there is no kind of time for any rearrangements. And so this is a concerted mechanism. So this kind of happens all at the same time. Again, once the nucleophile comes into the alpha carbon, the leaving group immediately leaves. And so this, again, is a pretty fast reaction. And so when we are looking at kind of how fast, we want to look at how good a specific reaction is of an SN2. And so the way that I like to visualize this is almost like parking your car in a parking spot. So there are some things that definitely help and speed up the process, and there are some things that will make it a lot more difficult to complete the parking in a parking space. So if we have a small nucleophile, that basically will help kind of maneuver it a lot easier into the sigma bonding anti-orbital. And so it's kind of like if you are trying to park a huge truck versus a compact car. It's a lot easier to park the compact car because it's more maneuverable. And so if the nucleophile is really big, it's going to have a hard time getting to the sigma antibonding orbital. And then the next thing is the strength of the nucleophile. If we have a strong nucleophile, it will kind of go through an SN2 mechanism. But if we have a weak nucleophile, it will not go through an SN2 mechanism. So if we have something like water, we won't go through it. And most of our strong nucleophiles will have the negative charge. They'll be anions. And so the next important thing is the open electrophile. If we have a leaving group that is very sterically hindered, it's kind of similar to the small nucleophile. It's going to be hard to maneuver around all of those sterics in order to attack the sigma antibonding orbital. So if we have like a tertiary alkyl halide, we will not do SN2 because it will be too sterically hindered for the nucleophile to go in and attack. And then the next point is the solvent that we use. And this is kind of less important. This is always kind of what I consider at the very, very end. And so what we want is a polar aprotic solvent. And so if we were to come over here and we have our electrophile, we have our nucleophile, if we had a protic solvent instead of an aprotic solvent, what that basically means is that our solvent is able to give up hydrogens. And so what will happen is, we can have this strong nucleophile interact with our electrophile, but in reality, we can have our strong nucleophile interact with the solvent. And in this case, it may not have been the best example just because we would have created water and something else. But if we have something like, actually, I'll just go ahead and fix this really quick. So if we had something like NH2 or NaNH2, that will be, like a strong nucleophile. But if we introduce a protic solvent, it will actually just go ahead and deprotonate that solvent because we're in a sea of solvent. There isn't necessarily as much of this electrophile. So statistically speaking, our nucleophile will bump into a part of our solvent. And if it can react with the solvent, it will. And then we would get something that is not as nucleophilic because it won't have that negative charge. And so again, this is not as important as kind of the previously mentioned, but it is kind of a factor that you could consider if it comes down to that. And then kind of the last important thing to consider when we do SN2 is we really want the leaving group to be stable. So if we kick off the leaving group and it's really upset that we did that, we're not going to go ahead and kind of go ahead and do the SN2 mechanism. And so a lot of times you'll see that if we have something with a water or an OH group, if we kick off this OH group, it becomes a hydroxide anion. So you guys probably remember from Gen Chem that this is not very stable. It reacts pretty violently. It's a strong base. And so we will not follow that reaction mechanism because our leaving group is not stable. And so when we kick it off, it's going to complain. So we're not going to go through with it. And then just kind of a few important things to consider when we have SN2 is we have an inversion of the groups. And what that basically means is that when we have, our electrophile, if it looks like this, and we have our nucleophile attack, the electrophile kind of goes in reverse. And so we can see that if we are looking at, maybe something like this. So if our nucleophile comes in and attacks and kicks the chlorine off, we will now have this arrangement right here. So the methyl group is still coming at us, but instead of kind of being to the left, it's now to the right. And so a lot of times when we have SN2s, we will see that the the absolute configuration of the chiral center changes. That's not always the case, but for most of the cases, it will change. So when you have an SN2, just kind of make sure that you are double checking that the priority did switch. And then finally, the rate of an SN2 is based on both the concentration of the nucleophile and the electrophile, and that is kind of why it's SN2, because we have both of those concentrations playing a factor in the rate. So hopefully that made a little bit more sense. And again, I always like to go back to the parking the car visual because that really helps me figure out what's important, what is good for SN2, what is bad for SN2, and stuff like that. And I just have like a few practice problems that I'll kind of walk through, and then we can, hopefully get a better idea of how these reactions work. So a lot of these will kind of have the same electrophile just because I want to look at different things. But with this, we have NaOH, which will dissociate into sodium plus and hydroxide. And our hydroxide is going to be a strong nucleophile. And so it will attack, and there will be an inversion of stereochemistry. And then our bromine leaving group will be chilling with the sodium plus. So this one will do SN2 because we have a pretty available electrophile, a strong nucleophile, polar aprotic solvent. Everything is basically good. And so for the next example, we have another alkyl halide, and we have sodium acetylide. And so that will be this once it dissociates. And hopefully you guys can recognize that this is actually our acetylide substitution. So when you guys learn that, you were kind of learning an example of an SN2 reaction. And so what will happen is the acetylide will attack the alpha carbon and will kick the bromine off, and it will look like this. And then always count your carbons just so that you make sure that you have the right number. 5, 6. 1, 2, 3, 4, 5, 6. Good. All right. And then with the next example, we have some electrophile, and then we have some sort of thyroxide, I think. But so when we dissociate this, we have a strong nucleophile, but we don't have a good leaving group. So this OH is not a good leaving group. If we kick it off, it's going to be pretty unstable. And so another kind of way that you guys could look at this is following the negative charge. So we don't want to make a structure that is more unstable or something that's basically the same stability. We want to end with something that is more stable. So with the first example, we have our negative charge on this OH, but on the right, we have it on a bromine. And so that will be favorable because the bromine is better equipped to handle that negative charge. If we have this second example, we have a negative on a carbon that's pretty unstable, but when we go ahead with the SN2, we put the negative on a bromine. So that's good. If we were to kind of go ahead and complete this, we go from having a negative on a sulfur to a negative on a water, or I'm sorry, on an OH. And we know that the sulfur is more equipped to handle that negative charge. And so this will not have a reaction because our leaving group is not very stable. And we're basically shuttling the negative charge from something that would be more stable to something that's less stable. And so, there's no point in doing that. And then the next example, we have sodium cyanide. And this will go ahead and attack the alpha carbon. But this alpha carbon is very, very sterically hindered. It's like trying to park in a space that has two people next to you. You would rather park in a space that has no one next to you because it's a lot easier to maneuver. So this will also have no reaction due to a tertiary halide. And this one will not have a reaction because we have an unstable leaving group. And then for the next example, we have the same electrophile and we have water. But like I mentioned before, water is not a strong enough nucleophile to do SN2. There's kind of like a cap. You have to be stronger than a certain point in order to do SN2. And if you aren't, you may do SN1. But in this case, water is not strong enough to do SN2. So we will not have, actually, I should be saying no SN2, sorry. So for all of these, we will not have an SN2 reaction. Because again, water is not a strong enough nucleophile to go in and kick the bromine off. Because, if we were to do this, again, we can kind of follow the charges. We would have again, this is not correct, so don't kind of follow this. But if we were to do this, we would have no charge. And on the right, we would have charge. And so again, that's not kind of electronically favorable because we are going from neutral species to having charged species. So that really is not going to happen. And then for this example, this one is a little bit interesting. I'm not really sure, depending on your teacher, if they will kind of test you on this. But with nitrogen compounds, they are strong nucleophiles. They don't even have to be minus charged to be strong nucleophiles. So even ammonia will be strong enough to really do SN2. And it's kind of hard because, at this point, we're kind of on like a sliding scale. So we're, able to do SN2, but it may not be super duper awesome, if we compare it to sodium cyanide or like sodium acetylide. That is really good SN2 because we have a strong nucleophile and a very kind of open electrophile. But as we maybe make a secondary electrophile, how do we kind of differentiate which nucleophile we need? And that kind of just depends on your teacher. But when we have something like ammonia, it is a strong enough nucleophile to do SN2 most of the time. And so we will get this structure right here, which will be positively charged. And so Again, there isn't really like a super duper clear line in the sand because I've seen textbook problems that do something very similar to this, where they have ammonia attack a halide and they say that it works. But in this case, the ammonia will stay protonated or will require another ammonia to become deprotonated. But the bromine won't necessarily be the one that deprotonates it. So we would have to have another ammonia come in and basically deprotonate, and then we would be left with this NH2, bromine, and an ammonium to conserve charge. And so again, just depending on your teacher, but it is kind of nice to know if you have to do some sort of synthesis and you see that it looks like it's going through an SN2 with ammonia, it could happen. So for the next example, we have the same electrophile, but in this case, I kind of went a little bit dramatic with the nucleophile. But this is just kind of going to show you that sterics of the nucleophile are also important. It's not just the sterics regarding the alpha carbon, but also the nucleophile. So if we have a giant monster truck trying to park in a space, it's going to be a lot harder to maneuver rather than if we just had, like sodium hydroxide, which is much less sterically hindered. It's going to be able to maneuver a lot better. And so this will not have an SN2 reaction. And so with the final example, this is kind of talking about epoxides, and depending on where you are and how your teacher decided to order the content, this may have already been brought up, but if not, it's not necessarily super important that you know what an epoxide really is. But I just find it helpful to visualize what is going on from kind of like an inversion of stereochemistry / group standpoint. So we have our strong nucleophile, and just kind of with epoxides, if we have a strong nucleophile, we go to the less hindered position. And so we have 2 carbons right here, 1 and 2. And so we have on the right just a methyl group and on the left an isopropyl group. So the right is less sterically hindered. So what will basically have happen is the hydroxide will attack that carbon, pop open the epoxide ring, and leave us with a structure like this. And the reason I really wanted to go over this example was because I think a lot of students want to say SN2, I need to flip wedge to dash and dash to wedge. That's not always the case because we have these groups that are kind of going down and my thumb is still pointing at me. But when we attack with the hydroxide, we just flip them up. My thumb is still pointing at me, but it's still going up. So in this case, the methyl group was down and on a wedge. And on the right, it's up and on a wedge. So we did technically invert the stereochemistry at that carbon, but we're still showing the methyl on a wedge. So don't necessarily always say wedge dash dash to wedge with SN2. Make sure that you're looking at the configuration of the chiral carbon and seeing that maybe changed. So that's really all I had for this video. I'm going to try to do one for SN1 E1 and then one for E2 and then one to kind of put them all together. But if you have any questions, feel free to reach out. Just let me know.